This is a Matlab program to price an American call option. And we're going to use here an explicit method. Actually, we're going to do that. We're going to compare both European and American call options, and we're going to calculate both at the same time here. And as you will see, actually there is just one little difference between both. There is one order of difference, so one common line that's going to be different when evaluating an American call option. And we're going to do that as including a dividend yield for the underlying. So the structure of the program is actually going to be the same as the one we already explained to evaluate the European call option using the same explicit method. So here at the beginning we have the parameters of the problem. Here we have the interest rate, that's the volatility of the underlying sigma. That's D, capital D, it's going to be a continuous dividend yield associated to the underlying. Here NT is going to be the number of time steps, and S is going to be the number of asset price steps. Here S max is the maximum asset price that we're going to consider. The minimum one, in this case, is going to be 0. The time for maturity or the expiration of the contract, the strike price, in this case, is going to be 10. Of course, you can change all these parameters as you wish here. Then considering that t is the maturity time and the number of time steps in nt, then the time step is going to be t over nt. In the same way, we can define the price step here, ds. So here we are going to initialize the matrices we have for the option values. We are making all of them 0. Then considering the time step and the price step, we have discretization, the asset and the tau variables. Remember here that the time variable, as time goes backwards, in order to consider that instead of final conditions, we are including initial conditions for the tau variable. So the tau variable is going to be the capital T, the maturity time, minus natural T. So in this time variable, initial conditions are going to be the payoff, but first we are going to discretize both S and this tau variable. So this is the one that this discretization of both these variables, considering asset, the price step and the time step we have defined before. Then the initial conditions in this tau variable we're going to prescribe here. So basically they are the call payoff at expiry, which means that considering it's a call option, then we have that the payoff is the maximum of S minus E or 0. So here we are defining it. As you can see here, the above defined, that's the initial condition. That's why we have an index 1 here. And we're going to define here, we're going to calculate V, it's going to be the European option, and V aim is going to be the American one. So of course, both payoffs are the same here. So then after defining these initial conditions, we're going to define here the boundary conditions here. These are the boundary conditions. In this case, I have to remember that we have to include the effects of the dividend yield associated to the underlying. So the initial conditions, both for European and the boundary conditions both for the European and American option. In the case the asset price is 0, then the value of the call option is going to be 0. That's why here we're defining the element of the V matrix of element corresponding to the index corresponding to the asset price is going to be 1, and for any time it's going to be 0, and the same for the American option. And then we have on the other side, I mean, when S is very large, I mean, S going to infinity, that for us we are considering here that considering that S max, when S takes the value X max that we have defined before, we are close to our effective infinity in our program, and that's going to be here the boundary conditions. In this case here, of course, here we have S times the exponential minus D times tau. This is tau, so we have the value of S but discounted with the dividend yield associated to the underlying here, and minus E, the discounted value of E considering the interest rate we have defined before. So here we are defining, here this is the matrix values corresponding to the index associated to the asset price, to the maximum one, ns plus 1, in both cases for the American, for the European one and for the American option, and for all different time indexes. And as you can see that they are all the same. So everything up to now between the European American options are the same. And now it's time to implement the algorithm here. So here we have again the time loop. Here we have the loop on the asset index here. Again, J is going to define the time index, and N is going to define the time associated to the index. And here we have the explicit algorithm here to calculate the value of the option, in this case the European option, at index associated to the asset n, and time j plus 1 as a function of different values of the option evaluated at the previous time step, time j, and then and evaluated at different values of the asset. So it's connecting different values of the option at the previous time step and asset indexes corresponding to n minus 1, n, and n plus 1. So this is the algorithm, and here it's important taking account that here we're including here the effect of the dividend yield, both here and also here, because basically the only difference is that the effective interest rate, which is affecting to the partial derivative of v with respect to s in the Black-Scholes equation, instead of being r, is r minus d whenever this dividend yield, the continuous dividend yield, is included, because all the rest is actually the same. So again, as here we are including the effective dividend yield associated to the underlying, we have to consider the finite difference method for the slight extension of the Black-Scholes equation, the one including the effect of the dividend yield. So here we have this finite difference method for the European call option to evaluate the European call option, and here we have the same actually for the American one. So what's the difference between the two? So the only line which is the difference between the two is this one, where here, as remember, the difference between the European and American call option is that you have the possibility of early exercise. So in order not to be any arbitrage, you have to check if early exercise is better for the American option. So you have to check. So the key thing in order to price the American option is that the value of the American option cannot be can never be lower than the payoff. So because otherwise there is a possibility of arbitrage, because in the American option you can always have the possibility of early exercise. So here in this line you are checking actually if the value that we have just calculated here is actually lower and higher than the payoff, and you are taking the maximum of the values that we have calculated before and the payoff in order to avoid the possibility of arbitrage. That's actually the only difference. If instead of being an American option that it gives you the possibility of having early exercise at any time, it's another one which, for example, it's a Bermudian one which has some fixed dates that gives you the possibility of early exercise. So you have to do this check not at any time, which is included in this loop here. We are making this check here for all different j's you have here in this loop. So instead of doing that at any time, you have to do this check here in case you have these Bermudian options at the specific dates that giving you the chance to making this early exercise. That's the only difference that with respect to the European one. Okay, once you have calculated all the different values of the both, in this case, European and American options, it's time to plot the differences, and actually here we're going to plot both the European and American options, and we're going to use the dashed lines for the European ones and solid lines here for the American ones. And we're going to plot both European and American at three different times. Tau equals 0, a half time, and a tau equal capital T, which basically means that at the time of the contract. And we are going to use different colors for that. We are going to use a red color for tau equals 0. We're going to use a green color for intermediate time, and we're going to use the blue color for the time at the time of the contract. So it's already time to make the calculation to plot the program here. Okay, sorry for that. Going to do okay. Okay, so we're going to run the program, and that's actually the result that we have. Okay, again, there's the dash line. Sorry, the red line here is the payoff. And remember, solid lines are the American ones. So you can see here, that's a green line here. This is the blue line, which shows the value of the option at the time of the contract here. As you can see, they are always higher than the payoff, basically. And on the other hand, in this case, due to the effect of the considering the continuous dividend yield in the underlying, you can see that the value of the European call option goes lower than the payoff. These are the values, dash lines correspond to the values of the European call option. So once you have this plot, of course, you can also calculate the specific values considering the value of the asset price at the time you are making the signing the contract. So here basically we have seen the Matlab program in order to deal with these open boundary conditions. In this case, we have priced the American call option, and actually we have compared that with the case of the European one. As you can see, there are just one difference, one common line different in the program, the one where we are checking actually if it's the possibility of early exercise here is better or not here. That's the line which makes the difference between the European and the American one.